Students, welcome to the fourth class of nuclear physics. We have been doing mass defect in our last class. So let's start from the point where we stopped in our last class. We were here. So we had an atom which had Z protons and obviously A minus Z neutrons. So this is an atom, this is the nucleus, and obviously so we'll also have Z number of electrons. So the total mass of this atom when measured is this much. And what are these? These are the components, the masses of the components. That means I measure the masses of the protons and the neutrons and the electrons, and when I add them, this is the mass. So this should have been equal, but no, it's not equal. There is a difference. It is as if when the masses of all the constituents are added together, then the mass seems to have been lost, because you see this one is smaller than this whole. So this quantity delta M is called the mass defect, which you must be familiar with. Now this delta M, where did this mass go, was a question that seemed to have bothered the scientists during that time. But then Einstein's mass energy relation was like this, that if I have got a quantity of mass delta M, if I have a quantity of mass M, then it is equivalent to an energy mc square, like this. That means the mass M can be converted to energy, and how much energy do we get? We get this multiplied by c square. So that means the mass that has been lost has been converted to energy, and this energy is responsible for keeping those nucleons and the nucleon, that means the protons and the neutrons, very closely packed together. So do you remember we were wondering how these particles are so strongly bound inside the nucleus? So this mass that has been lost is responsible, and this is called the binding energy. Not this mass, but the energy. So if this is the mass delta M, then the binding energy would be delta M into c squared, which gives us ZMH plus A minus Z Mn minus AMZ, so into multiplied by c squared. So we have already seen the mass and energy conversion before. We know that one atomic mass unit, which is denoted by small u, is equal to 931, is approximately equal to 931 ME, million electron volt. So this is the relation. So you may have numericals, and we will try numericals too. So now let us proceed further. Let us move on to something called the packing fraction, which has got some importance in nuclear physics. So what is packing fraction? So packing fraction, it is denoted by small f, and it is equal to AMZ. And what is AMZ? AMZ is the mass of the atom minus A. So this is divided by A. This is said to be the packing fraction. So you will have to remember a few small terms like this. So this is the packing fraction. We learned what is the binding energy. Then so we can write this as excuse me so F is equal to AMZ minus 1, which implies what is AMZ? It is equal to 1 plus this. Now this quantity, this is said to be the mass excess. So it is the mass excess. Please don't confuse it with the mass defect. This is mass excess. Which portion? This one. So we learn what is binding energy. We learn what is mass defect. We learn what is binding energy. We learn what is packing fraction and what is mass excess. Now let's move on to something else, something very important. Now binding energy we had written as, is generally written as B. In some books they may write as EB, but I'll be using B here. So what is B? B is the binding energy. So binding energy, we already know what it is. We have found the expression. We know that binding energy is equal to ZMH plus A minus Z Mn, mass of the neutron, minus AMZ into C square. Now binding energies are sometimes also expressed as in terms of mass. If I express in terms of mass, then what will happen? I will not have this C square. I will not have this C square. So in mass units. So if I write it like this now, let us divide this by A. So let me write it here itself. So it becomes like this by A, and this divided by A. So this quantity, look at this. What was B? B was the binding energy of the whole nucleus. That means it's the force by which, it's not the force, it's the energy by which the nucleons bind each other. Okay, if that is the total binding energy, then what is B by A? Try to remember what is A. A, is it not the number of nucleons, because it's the number of protons plus the number of neutrons. So A is the number of nucleons. So what would then this be? This is called the binding, this is the binding energy per nucleon, and this is denoted by B bar. So what is B bar? B bar is nothing but B by A. It is the binding energy per nucleon. So this would be Z by A, as we have already written, mass of hydrogen, plus this would be 1 minus Z by A mass of neutron minus 1 by A m Z. So this is like this. So I can take Z by A common out here. So what do I get here? This is mH minus m n plus mn because of this one plus mn minus, now what is this? If you remember, it is nothing but 1 plus f. We had written it just now. F is the packing fraction here. So this is equal to Z by A mH minus mn I'm sorry, I shouldn't have written it again here. Now you see these are mH, mn. Mn is what? It is the mass of the neutron. mH is what? It is the mass of hydrogen. So these are known quantities. What is unknown here is Z and A. Because with different nucleus, different elements, Z will be different and A will be different. So we have here this as when you put the values, you get here minus Z by A zero point 0.0008 397 plus 0.0086649. So minus F. This will be like this. So what do we get from here? What do we come to know from here? Let's see what we know from here. This is the binding energy per nucleon. From here, it's obvious that the binding energy per nucleon, I'll write it down here, B bar, that means is maximum. When is it maximum? When F is minimum. Obviously, because F is being subtracted. Maximum when F is minimum. So this is one thing, and then we move on to something very important, which is called the binding energy curve. So what is the binding energy curve? That we'll see just now. Let's look at the binding energy curve. So suppose we draw a graph. Between the mass number and the binding energy per nucleon. So that means we take different A, definitely different elements and different isobars actually, and then after that what we do, you plot B bar here. So what is this? This is the binding energy per nucleon and this is the mass number. So we get a graph like this. We get a graph like this, which is called the famous binding energy curve. So we'll talk about it, we'll discuss this in the part B of our class today.